Welcome to the statistics course. It's nice to have you here. The purpose of this is to we gotta walk before we can run. I want to do like data science and machine learning, and before we can do that, we have to do statistics. So this is where we start. If you like the video, like it, comment, or subscribe. Nice to have you here. So the first thing you need to do is go to the GitHub and download this Jupyter notebook file, this Python file, and I have it opened in Google Colab. So if you don't know how to do that, I'll post like a link to do that. But yeah, so I have this thing in Google Colab, and we have our statistics thing broken down into 5 different sections. And let's start off with the probability. Okay, so we're starting here before we get into let's start with the definition of statistics, actually. We'll start up here. So statistics, I defined it as the science of the collection, interpretation, presentation, and prediction of data. Pretty much you're just using, it's like you're just manipulating data to show different things. And then in terms of the code, I have all our imports in here, all our modules. So we imported NumPy, we imported SciPy, Matplotlib, scikit-learn for the models, and then the math module. Okay, let's start off with the probability. I remember taking this stats course in college. We have to learn about this before we can go over anything else, just to, because if you see this formula for the Bernoulli triangles, that pops up down here. So let's start off probability. It's the likelihood that an event will occur. And what's an event? We have to go down to the experiments. So an experiment, it's a procedure with a well set of defined outcomes, and it can be repeated. A trial is just one run of an experiment, and then an event is the outcome of an experiment. So up here, the likelihood that a given event will occur refers to that. And probabilities between 0 and 1. Down here's we're going to talk about sets first. And this entire box, you can consider it a set of objects. And then A and B are elements within the set. And then you can see the intercept is this. So this little symbol means intersection. And you can calculate intersection by doing either A times B. That's how you get the intersection. And then if it's like conditional, we'll talk about that in a second. You can use this formula to solve it. Okay, the union is the two of them together, and they can be the elements of the set. They can be exclusive, meaning they don't interlap, or they can interlap. And here are the formulas for the two. You either add it, or you add them and then subtract the middle, the intersection. And there you go. It's the union. So now let's move on to conditional probability. And that's the probability that something will occur given something has occurred in the past. So an independent event, that's when the probability doesn't really depend on the past. But in this, with conditional probability, it depends on the past. And you use this symbol, this given, it means given. So you can calculate the probability that A has occurred given B has occurred. And you do that by dividing the intercept of, or the intersection of A and B by the probability of B. And then you can also rewrite this as if there's more than just A and B, the intersection of probability of A times the probability of B given A times the probability of C given A and B occurred. Okay, and then Bayes' theorem is this is used in like medicine when they're doing like ages, the probability of like having a disease given you're this old. That's used often with Bayes' theorem. It's when you have one probability but don't have another. So the probability of A given B is equal to the opposite, the probability of B given A, times the probability of A over the probability of B. And then here we have just like a representation of B. So I'm going to move on from sets, and then we're going to move on to this thing called combinatorics. If you've taken any math classes, this is like where they bring out all the card games and stuff. This was a really annoying part. I think it was finite or something like that. So combinatorics, that's just about all the different combinations or arrangements of things. So there's really two things you need to know. Permutations, which is when there's a particular order. You can think of like a race where you have 10 people and there can only be a set order for first, second, and third. And then combinations, there's no particular order. Think of it like you're picking people to be on your basketball team or whatever, your football team. There's no order. It's just you have 20 people. I'll pick this guy, I'll pick this guy, I'll pick this guy. There's no first, second, or third. And there's two formulas for each, with repetition and without repetition. So that means you can think of like with repetition, like the same guy can like win, but like with no repetition, like it can't be like, it has to be a different person each time. Okay, so here's the formula for no repetition. Repetition, I got this formula. This is a different formula, but I just got these formulas from Google. That's it. So the with repetition is just n with r as the exponent. That's it. And then we have that function. And then no repetition, it's this formula. With combinations, I should probably tell you the notation. Okay, so n is just the total number of like things you can select from. R is the like amount, like how many things you're selecting. So if you have 10 people running a race and there can only be 3 first, second, and third, 3 podium members, 10 would be n, and then 3 would be r. And then n factorial, of course, it makes sense. So that's the total number of permutations. Okay, so combinations, it's similar, except you add this r factorial term down here. And this is the formula for no repetition. And then here, this is the formula when you allow repetition. Okay, finally, we're going to end probability with talking about Bernoulli triangles. It really refers to an experiment with 2 possible outcomes. You can think of flipping a coin. That's like the most common one. So it can either be heads or tables. And you're probably like, what is this symbol, n over k? It just refers to this, the combinations. That's all it refers to. Math notation can be confusing. So P is probability, K is like the event, and then this Q is just 1 minus P. It's the probability of the event not occurring. And down here I have a sample calculation, so you can see that. And then Bernoulli triangle, or not Bernoulli triangles, Bernoulli trials, they'll pop up in terms of somewhere down here in the experiments. But you'll see this formula again. Okay, so we're done with probability, and you can always go back to these notes to reference them since I have it on the GitHub. It's free to access. Let's go over data now. Now, data is just a bunch of collected observations on something. You can have data on golf clubs or bed sheets or whatever, like whales, I don't know, just collected observations. And you have to get the data, so you can do that through experiments or just observing things. So there's two sets for data. There's the population, and that refers to every member of a particular group you're studying. So if you're performing an experiment testing a drug on cancer patients, the population will be like all the cancer patients, like in general. And then the sample will be, it's just a subset of the population that you're measuring. So the subset of that will be the actual patients, cancer patients that you're testing your drug on. And types of data, you have continuous data. So infinite precision, you can think of like decimal points and stuff. And then finite precision, discrete, you can think of like integers, like 1, 2, 3, and then categorical categories. So, here's like a categorical thing. Nominal is categorical. Levels of measurement. So predetermined categories that can't be sorted. You can think of political parties. Ordinal, sorting categories that lack a numerical scale. So colder, coldest. If you've taken like standardized tests and like the always, sometimes, never, that's another ordinal scale. Interval is just a numerical scale with no 0 point or floor. So you can think of a temperature, it can be both positive and negative. And then ratio values with the 0 point. So like age, you can't be -1 weight, and then salary. Okay, now now we have like basic ways of categorizing data. Let's go on to see like where the data is, and that's measures of central tendency. That's like the location of the data, so it's like in this spot. And there's 3 measures of central tendency: mean, median, and mode. You guys probably know this. You guys have been doing this since like grade school probably. So calculating the mean is just you sum up all the values of a data set and divide by the total number of values. And then in code, remember we imported all this stuff. You can do this np numpy.mean on the data, and that gives you the mean. Median is the middle value. It's good when outliers are present. So np.median on the data. And then you can see it cuts out that outlier. So if we used the mean, it would have messed up the data, the outlier would have messed everything up. So we use the median there. And then the mode is just the most common value in a data set. So we have our things here. And then we have the stats.mode going up to scipy. Stats.mode on the data. And then this gives you this array. So the mode is 6 because 6 is the most common value. And the count of everything is 7. So 6 sevens or 7 sixes. 1, 2, 3, 4, 5, 6, 7. Okay, moving on from measures of central tendency, you have measures of dispersion. And this is the general spread of the data. You have the range, so that's the maximum minus the minimum. Here I have our data. It's a lin space from 1 to 100, and there's 30 values. So minimum value would be 1, maximum would be 100. So the range is 100 minus 1, which would give us 99. And then if you don't know Python, this is just like the notation to get like the last value and then the first value. I can link the Python thing in the description. Okay, so moving on from range, we have variance, and this is the equation for variance. And so we have another thing, just like here, 30 values going from 1 to 100, and it's lin space, it's normally distributed. We'll get to that in the future, so they're like equally spaced. But like to get the variance, I did this stats.describe. This goes back to SciPy. Where are we? Here we are. So you can see you have all these values with like kurtosis. We don't need to know that, but that refers to like the peak, and it gives us the variance right there. Okay, you can also use this thing to calculate the variance, this t-var on the data. T-var means trimmed variance. They cut out all the outliers. And there you go. And then finally, standard deviation. That's actually the square root of the variance. And that's the formula. With the standard deviation, you also see like a delta symbol there too. So yeah, you square it. And with like standard deviation, that's pretty much the average value between the data points. So from this value to that value on average, it's that. And then you can calculate the standard deviation with this t. That's STD data, trim standard deviation, and that's it. And then I talked about outliers in terms of like the mean, median, mode. So like how do you calculate an outlier? Well, we have these things called quartiles, and we'll divide a set of data into 4 different parts. We'll so you divide into 4 different parts, and then we can calculate this thing called the interquartile range, the IQR, and that's like the value for the quartile 3 minus quartile 1. And then based on that, we can come up with a boundary, and then the first part of the boundary is quarter 1 minus 1.5 times the interquartile range. That gives us the boundary. And then the other one is quartile 3 plus 1 times the interquartile range. So that gives us our boundary. So with our data, we have our data set, and then we calculated all the quartiles. It says mp.quantile, and then I made it a quartile because it's 0.25. It's the first part, second part, third part, and then fourth part. Okay, so there we have our quartiles. And then we can also calculate the IQR again with the stats.IQR on our data. And that's 92 minus, 92.5 minus 37.5. It gives us that. And then, man, I'm kind of sick. Sorry, guys. But finally, with you can plot this out using a box plot with the data, and you can see it gives us our I think that's the median, and then quartiles, like in here, and then boundaries. So yeah, and then you can see if we go back to our data, I had 300, and it's all the way out here. It's way outside the boundary range. Okay, finally, okay. So now we're going to talk about correlation. So that's just a relationship, and correlation does not prove causation. I always go back to there's more golfers in the summer than winter. And then there's also more ice cream sales. So ice cream does not cause someone to play golf. So even though the events are correlated, that does not prove causation. Okay, so bivariate analysis, that goes up with correlation. This is one way to look at correlation. You set the x value or x-axis to the independent variable, set the y-axis to the dependent variable, and then you look at how they're correlated. So you're comparing 2 variables with bivariate analysis. And then you can see, with this we have a housing thing that I made up. So number of rooms correlated to the price of the house. And as you have more rooms in your house, look at that, the price goes up, positive correlation. Another way to look at correlation is this thing called covariance, and you're comparing the variance between two sets of data. And then from like a positive covariance, you can infer that positive correlation and vice versa. This is the formula. So like that. So like X and then Y, one value, like one data set, the other data set. This is each number in the data set for the X. This is each number in the data set for Y. Mean, I think this is the sample mean. Yeah, sample mean, and then sample mean for Y. And then, total number of values. Okay, we'll talk about this in a second. Okay, so we have an array with our two separate data sets. There we go. And then it spits out, when we do the covariance on here, you can see we have one formula. However, it spits out 4 different things. You're probably like, what? Why? It's because it gives you this covariance matrix. So it's comparing the covariance from X and X, when like X, Y, X, that X and X, X and Y and X the reverse, and then Y and Y. So so that's our covariance matrix. If you just wanted one value, you could just take that out and just compare it like by itself. Okay, so finally with correlation, this is really cool. You'll probably like this. So you're probably thinking like, okay, like how do we get like a normal value, like almost like probability, in terms of correlation? Well, you use this thing called the Pearson correlation coefficient, and it's normalized, so it's adjusted so that everything's on a common scale, -1 to 1. 1 total correlation, net positive, -1 total negative correlation, 0 no correlation. And this is the formula. So the summation of, remember, like x1 refers to like a value in here, y, value in there, first data set, and then that's the mean. And that's all I need to talk about. Okay, yeah. So you can calculate that by the stats. Again, that goes up to SciPy. And then it's the Pearson R function, and then you give your 2 different X and Y data sets. So it gives you 2 values. This is what you want, this first thing. And it says they're 98.9% correlated, and you can see up here, yeah, they're pretty correlated. Okay, so there we go. So I think that's it with data, which is nice. We're getting there. I really want to get to models, because that's when you finally get into like the AI, machine learning stuff, which is what I'm really interested in this, but we gotta walk before we can run. Okay, distributions, it refers to the spread of the data. It's like all the possible values in a data set. And it kind of goes with like the dispersion. Okay, we're going to talk about some really basic distributions. So binomial distributions. So there's 2 possible outcomes. Again, like heads or tails. That's it. And this is the formula for the function for it. And I just want to draw your attention to, if you're paying attention, this formula looks a lot like the Bernoulli, that's not it, the Bernoulli triangle formula. It's pretty much the exact same. So that's where this comes from. And remember, this is the number of combinations going back from combinatorics. Okay, and then the P, probability, Q, so 1 minus P, and then it tells you everything. So to calculate this value, you can do this stats.binom.pmf, and then you plug in X, N, and P. And there we go. And then here I have it plotted out. This is how a binomial distribution typically looks. And then going off that, we're going to do a normal distribution or a Gaussian distribution to look fancy. This you have to know. You have to know the normal distribution. It's the bell curve. If you've taken like any like science course at all and you see that graph, you know, like with like all the percentiles and stuff, this is what they're showing. This is the normal distribution, the bell curve. And there's equal measurements both and above and below the mean. Okay, and then here's the formula for it. Remember that standard deviation down here. And then, yeah, it tells you everything. Okay, good. And then this E, it's on your calculator. It's like a constant, pretty much like pi. Okay, so here is the normal distribution plotted, the bell curve. And then going off this, you have this thing called the central limit theorem. Woo. And it just says that 95% of the sample mean should fall within 2 standard deviations of the population mean. So most of your data is going to be within here, within 2 standard deviations. And then the mean values will be normally distributed, of course. Yeah. Okay, going off that, like you'll often see things are divided up into certain percentiles, so like 90th percentile and stuff. And you also see that with like test scores, like medical stuff, I don't know. Or like if you've been to college, like SAT scores. So percentiles, how do we calculate percentiles? That's the definition of it. So you pick a value. Okay, so like any one of these values. I probably shouldn't have wrote that because that probably just confuses people. But you have a value, like an x value, and then you calculate the z-score. So it's the value minus the mean divided by the standard deviation. And then you'll look up the percentile in a z. You can either calculate it with this, or you can look it up in a z table. And here's a z table. Just says that's the z score you calculated. This is the percentile. Okay, so you can also use Python, SciPy, again, stats.percentile of score. And then this is our data set, our ACT scores. And then this is the value we want to calculate, this 27 that I plugged in. And you're at the 76th percentile with that score. Okay, so that's how you calculate percentiles. Yeah, so you can do some really cool stuff with, we're on experiments now. Okay, now we start getting into the cool stuff that I'm actually excited about. Experiments. So, yeah, you're always going to want to run experiments. And an experiment procedure with a well-defined set of outcomes. It can be repeated. Trial, single run of an experiment, event, outcome of an experiment. So, like, you want to see that your experiments work. So this is it. This is how you do things. So sampling, that's how you get data. You can do random sampling to avoid bias, where each member of a population has an equal chance of being selected. Again, this is why we have stratified random sampling, because sometimes when like a population is really big, you can exclude entire groups of people, and that's not good. So with stratified random sampling, you like make sure that you pick someone from every group within a population. And then cluster sampling is kind of like another solution to the problem. You'll break down a population into groups and then randomly sample each group. And that's to avoid bias, which is systemic error introduced into an experiment. There's many types of biases. Like a very common one is a selection bias. And when you're sending out surveys and polls, you're favoring people who actually answer those polls and surveys. So like people who are more introverted or whatever, you probably won't get their opinions on a certain thing. So that introduces bias. And then standard error, you need this. It's the difference between the population mean and the sample mean. That's how you calculate it. And standard error of a sample. I think that's the wrong formula, but whatever. I'm tired. Oh well, sorry guys. But yeah, you need the standard error because when you're doing an experiment and you get data like from like a certain sample, sometimes there's a lot of bias and you can't generalize the sample data to the population. So that means your experiment is a failure because the data in the sample says one thing, and the data for the population who you actually care about says another thing. And then you can calculate this value through stats.sem with your data. Okay, confidence intervals. If you know what p-values are, you've probably also heard of confidence intervals, and it's just a range. Like if you have a value, it's just a range where that value is likely to occur. So 95% confidence interval. That means the confidence will like if you do an experiment 100 times, 95% of the time the value is going to be within like the data set. Like 5 times it won't, but 95% it'll be in the thing. And then the point estimate, it's really just, we have the definition there. No need to explain it. Okay, so how can we calculate confidence intervals with Python? So here we have our data set. It's just a range of values from 0 to 30, 1, 2, 3, 4, 5, so like 30. And you can calculate it with the stats.t.interval, confidence interval, and then our alpha. We want it to be a 95% confidence interval. So that's our alpha. And this df is just like our data set. That's our scale. So this is all extra stuff. You can Google what it means if you want. Oh yeah, here are the parameters if you want to like look at what it means. Now here is our confidence interval, our 95% confidence interval. So the value is likely to be, if you do an experiment 100 times, 95 times it's going to be between this value and this value. 5 times it's going to be outside these values, but 95% of the time it's going to be within these values. So this is our first boundary, this is our second boundary. Okay, hypothesis testing. This is fun. Now we get into like the stuff I'm excited about, like the models and the hypothesis testing. So when you do an experiment, you want to see if it worked. Does the data support the hypothesis? Yes or no? You'll have this thing called the null hypothesis. This makes things, I don't know why they did this in stats, but the null hypothesis just pretty much means that the independent variable has no effect on the dependent variable. It's all due to chance. It means your experiment did not work. So when you accept, when you fail to reject the null hypothesis, when you accept the null hypothesis, it means your experiment did not work. Like it's kind of flipped. It makes your head kind of spin, the first kind of times, which is annoying. I don't know why they did this, but they did. When you're doing like with the hypothesis testing, you'll pick an alpha value, and that's a level of statistical significance, so that the data just didn't occur due to chance. And a typical alpha value, it's 0.05, less than that. So less than 5% of data, it's due to chance. Yeah. And then you've also heard of like p-values. Like if you've taken a stats course and you've heard of p-values, you're like, wait a minute, like isn't like that like the p-value? The p-value is what you actually calculate. The alpha value is like what you set. You're saying like, okay, I want my alpha. If it's less than this, then it's statistically significant. The p-value is what you actually calculate. Okay, and a way to do hypothesis testing is with the student's t-test, and you're comparing 2 data sets. The process is you determine what the null hypothesis is. You just throw it in your head, and then you set your alpha value. Typically, it's this, or something like that. Or if you need it to be even less due to chance, you can make it like 0.01 or something like that if you really need it. 99% confidence. Then you calculate the t-stat, and then you use the t-stat to look at the p-value, and then you compare the p-value to the alpha value and say, like, okay, is the null hypothesis confirmed or not? Okay, and calculating the t-stat, it's this. That's the formula that tells you everything. So the mean, yeah. There you go. Okay, so like this is why this video is useful, because you can go back and you have the notebook, you can just use it for yourself to do hypothesis tests. So we have one data set and a second data set. And then t-test, IND, data set 1, data set 2, and then we get our t-stat and we get our p-value out of that. So print t-statistic, t-stat, and that's our t-statistic for these data sets. P-value, yeah, that. I've set our alpha to that. That's what I set the alpha to. And if the p-value is less than or equal to the alpha, we reject the null hypothesis, and we say it's very likely that the independent variable caused the change in the dependent variable. So pretty much, if this is true, our experiment worked, and we're happy. I know it's like confusing. We reject null hypothesis, but it means our experiment worked. I don't know why they flip things, And if this isn't true, that means we do not reject the null hypothesis that the change is due to chance. So our experiment probably didn't work, Here. And we calculate this. Our p-value is 0.8888. Do not reject null hypothesis. Yeah, so our experiment was a total failure. Wait a minute, that's why. Okay, yeah, you can see it's pretty much the exact same data set. So like nothing happened. So they're like, yeah, the experiment was a total do not reject the null hypothesis. Our experiment probably didn't work. Okay, so let's say you're testing two separate variables, and you want to see, like, you're testing two things to see if they make a change in something. So does let's think of something. Okay, yeah, you're testing two different drugs to see if it helps. Well, you want to see if the values are actually independent from each other. So like you don't want to test the same thing and then like conclude, okay, this works and this one doesn't. Well, it's like the same thing. So it's kind of a waste of time. And it's typically used with the observational studies, like chi-squared. And that's the formula to calculate it. Observed value minus expected value. Yeah. Okay, so we have, so we have our two data sets in here. Okay, you probably can't really see that. There's a comma there. We have two data sets, and I want to point your attention to this. Look at the data sets. Look at that number. Look at that number. Look at that number. They're the exact same. There's no difference. So, yeah, this is like what we're talking about. Are they actually independent from each other? Okay, we calculate contingency, stat, p value, the expected, or the observed and the expected. And that's our alpha, print our p, and again, like the same thing. And our conclusion was, because it's literally the exact same values, we accept the null hypothesis. It's the same event. They're not independent. So this would not be a good experiment to run. Okay, finally, what we've talked about, like when you're comparing two things with the student's t-test, what about if you're comparing more than two groups of data? You use the ANOVA test, the analysis of variance analysis. I forgot what ANOVA stands for. It's something like that. But you calculate the F statistic instead of the T statistic. And a way to do that is you have like all the data sets, of course. You do stats one way. It's your F thing. And you plug in your data sets, and then it'll give you your F statistic and your p-value. And that's a pretty good p-value. This experiment probably worked. So I didn't do this because I was kind of lazy. I was really tired at this point making this document. So you can draw your own conclusions. And you should probably be, it's like common sense. Like if the p-value is less than your alpha, then you're good. Okay, finally we get to models. And after this is like our jumping point into AI, sort of. Yeah, so a model, so a function that maps a set of inputs to its outputs, and you can use it to make predictions. It's just a function. Yeah. Oh, I have to move. I have to get comfy. My back hurts, and I'm sick. Sorry, guys. But we're going to start off with this model, the most simple model. See formula below. Okay, I will talk about it in a second. Ordinarily, least squares equation to calculate b. Okay. Yeah, we'll get to this in a second. Okay, linear regression. Let's look at this model, this way to model data. If we go back to our data, if we go here, if we drew like a line in between there, that's pretty much what a linear regression is. You know, it's just, if you've heard of y equals mx plus b, that's pretty much what a linear regression is. That's the super secret AI function, and the linear regression is used in AI. And the formula for that is a y equals f of xb plus the error terms. And you can pretty much see it's y equals mx plus b. So like bx plus error, you know. And the error terms, it goes, I'm not going to explain that because it'll confuse you. You need to know a little bit more math to do that. Okay, yeah, so I'm just going to keep this simple. Okay, so this is our equation that like models the data. So y equals mx plus b, pretty much. And how do we calculate that? Well, how do we calculate the b value? We don't use the slope formula on this. This is a different way to do things. So when you're plugging in things, it's a matrix of different values. You typically do it in batches, so you do one set of data, two sets of data, and stuff like that. And you'll have your matrix of values, and then the transpose, like, how do I rate this? I probably should have taken a picture of this, but like, this is really easy. So if you've done matrix multiplication, you know you can write things like 0, 1, 2, stuff like that. Okay, you know you can have it like that. The transpose is, you know, when they're just like on top of like one another, like that. So you can multiply them if you've ever done matrix multiplication. That's what the transpose is. So it's like the flip version of this. So it's like this is, well, this isn't, I should probably make them the same values. Okay, so yeah, if you've done matrix multiplication and you see it's like the upright thing, this is the transpose of that. That's what the transpose is. And so yeah, you take, so you just do matrix multiplication, that times the transpose, and then you get the inverse matrix of that times the transpose again, and then the vector value of the response variable. Times y, your y stuff. Okay, so that's how you calculate b. So how do you calculate the error term? Well, you can use this formula. You can get the square of that. And if you see this SSR and this RSS, it's actually the exact same. If you go on Wikipedia, where are we? In here. Okay, yeah. RSS, SSE, See, RSS, SSR. It's the same. They screwed up. Let me go back. Yeah. I just want to show you just like so you don't get confused. Where are we? Ordinarily residual sum of squares. Okay, yeah. So sum of squared residuals, SSR. And if you click on this, SSR, it's that you get the RSS. So like they're confusing you, but it's the exact same thing that they're calculating. And you calculate it with this, the Y value of a particular data set, minus the X value, square, and you sum them all up. And then, yeah, you can calculate the error based on that. So yeah, that's how you calculate everything for the linear regression. This is the way of calculating the B value is called the ordinary least squares value, and then the error term is calculated using this. Okay. Oh, this would have been easier to do. Yeah, so now I'll actually take you to the process of doing a linear regression. And you have this. Then we reshaped it so that we can do the matrix multiplication. So like a normal thing would be this. The normal X would be this, but like its transpose is this. So this is just so you can do matrix multiplication, of course. And I printed out both the arrays. This is our X data, this is our Y data. And here I have a scatter plot for X and Y. So X values, Y values, and then model linear regression. I should have imported it here. That's the model we're using. And then we're model.fit X and Y. And then that's pretty much, it's like the model.fit. It's like, okay, perform the calculations, for everything to do that. And then model.score, R squared. This is I think this is the accuracy. I forgot what I did here. I think that's it, but wait a minute. Okay, yeah. So the intercept, which refers to the error term, the E, it's that, and then the coefficient, which refers to, what is that? I don't know who's here. It refers to that. Okay, yeah. So B value there. And then finally, you can use this to do a prediction. Remember the models. So we have this 26. That's what we want to predict. And then model.predict, and then we're predicting this value in particular. And then you need these two brackets because, remember, we're using matrices. It's like in between two things. Okay. So yeah, that's our prediction. So again, model, it's mapping one set of inputs to an output. And this is the start of our AI stuff. So I'm excited. We're going to move on to really basic AI and then deep learning after that. So I hope this statistic course is helpful. Again, if you need help, ask in the comments. If you like the video, like it and subscribe. And you have the code to yourself. So whenever you need this as notes, it's there.